This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay. Well, welcome everybody to the fourth of 4 lectures on de novo genome assembly. Today I'll be continuing with what we talked about on Wednesday. We talked about de Bruijn graph assemblies and how we can use this abstract mathematical concept of a graph to help us build a construct that we can then walk through and produce contigs from our reads after we've broken them into k-mers. So I'll just do a little quick, short, super short recap. Yes, blah, blah, blah. Remember, I talked a little bit about, back in the early days, they thought about using a chip to be able to detect whether or not certain k-mers existed in a sample and how that gave them the idea for assembly by de Bruijn graph. And then I talked a little bit about de Bruijn graphs and how they work and why we want to use k-mers, what k-mers are. And then we got into the examples of starting with some reads, breaking them up into smaller subsequences called k-mers of length k, and then how to take those k-mers and build a de Bruijn graph. And we went through the process of take a k-mer, split it into the k-1 and prefix and suffix, add both to the graph as nodes if required, and then add a directed edge to the graph connecting them, and then label the edge with a k-mer. And we went through some examples of building them, and then we talked about how we traverse this graph to pull out contigs. Like this, and we produced the word happiness, and then we got, we talked about Eulerian, yeah, that word, walk, Eulerian, and how we need to visit each edge exactly once to have an Eulerian walk, and that not all graphs will have them, and that's due to the fact that sometimes we need to make a decision as we're traversing a graph to build contigs, and we're not allowed to make things up, so we can't arbitrarily choose a path to go through a graph. So if we come to a decision point and we don't have any evidence to point us down one path or another, we have to stop calling that particular contig and then start again elsewhere in the graph and start building a new contig. And then we talked about the problem of repeats and how, with this example of Mississippi, how after we build our graph we get this horrible looking loop thing and we didn't know how many times around the loop we needed to go, and we can't have an Eulerian walk here because we have to visit the ISI k-mer twice, and that's probably not the, we can't really do that, and we don't know how many times to go around the loop, so we have to break this up into 3 different contigs. And then we decided to try and change the value of k and see if we could remove the loop. Unfortunately, it didn't remove the loop, but it also broke the graph up on us. And if you came to the tutorials during this week, where we played around with a real bacterial data set and then did a whole lot of assemblies using a de Bruijn graph genome assembler, where we gave it different values of k, and we saw the effect that that value of k has. And so at low values of k, so, oops, back this way. At low values of k, we get this nice connected graph, but we have these little loops and things. And we envisaged a thing from the law of repeats where if the repeat is shorter than our read length, or our read lengths are longer than our repeats, we can resolve them. So if we make the k-mers bigger, hopefully we'll be able to get to the point where we can resolve some of these loops and remove them from the graph. But we also face the problem where if we make the k value too high, we start to get disconnections in our graph, and the graph starts to fall apart into disparate sections. Okay, and then so I talked a little bit about why we had to choose k wisely, And if you came to the tutorials, you would have seen that there's this trade-off between connectivity and specificity. So having less ambiguity in the graph and having it still connected. And there's this trade-off, and there's an optimum value for k that we need to pick when we're doing a single k value de Bruijn graph. And then we'll talk a little bit later on today about other ideas. All right, so the first thing I want to do today is introduce read errors and what happens to our graph when we have errors in our graph, or errors in our reads, and how that affects our graph. So we've got these four reads: happy, innes, applin, and pinnet. And we get all of the three mers. So the k equals 3 k-mers, which is hap, app, p, inner, nes, s, apple, pli, lin, pin, and net. And we need to build a de Bruijn graph. So we take the k equals 2 prefixes and suffixes from each of those, and we build this graph. And as you can see, because of the fact that when we get to app and APL, they both share the AP prefix, but they have different suffixes. One of them has a double P suffix and the other one has a PL suffix. And so when we build the graph, we have to diverge. We have to have a divergence at that point. And so you can see we go from HA to AP, and then we diverge to PP and PL. And then it converges again when we get to IN, and then diverges again when we get to NE, ES, and ET. So, I mean, obviously we know it's meant to say happiness, right? But because the sequencing machine has made a mistake, all right, or there was a problem with our library preparation, or someone wasn't wearing gloves when they were handling one of the tubes and contaminated the sample with human DNA, which happens quite a lot, we get these issues happening in our graphs. So we get, yes, Grace. Yep, exactly. That's exactly how it works. And in about 3 slides' time, we'll go into that in depth. So, good thinking, though. Okay, so we have this graph, and we have all these bubbles and divergences in it, which are caused by the errors in the reads, or the contamination in our sample. Okay, so when we go to pull out contigs out of this, obviously we start with the HA and go to AP, and then we can't make the contig any bigger because we have to choose which path to go down, and there's no evidence to tell us which path to go down, so we can't choose, and so we have to stop. And then we can make another one appin, going from AP to PP to PI to IN, and we can make another one applin, going down the bottom path, and then inner, and then nes and net. Okay? Does that make sense, everybody? Right, we can't make stuff up, so we can't arbitrarily choose a path to go down. All right, now how are we going to go about fixing this? And Grace was right. We're going to, with Illumina, we get lots and lots of copies of all of these different reads, and hopefully the error won't be in all of them. In fact, it'll be in such a small minority of them that it should stand out. And so most of the reads are going to be error-free, and if we count the frequency that each one of these k-mers occurs originally and annotate the graph with that frequency, we can have some evidence that will help us choose which path to go down through the graph. Okay? So let's have a look at that. Here we have the same reads, except that the correct ones this time, the happy and the innes, are repeated more times than the error. Okay? So we have 3 copies of the correct reads and only 1 copy of the incorrect reads. And so when we take when we create our k-mers, our k equals 3 k-mers, we annotate how many times each one of them appears. Okay, and then we build our graph from that, and we get this. Okay, so we have HA to AP, and then obviously you can see there that now we have some actual evidence as to which path we probably should go down, and knowing what we know about the way sequencing machines work, and the fact that there are going to be error prone, and that the errors are going to be small compared to the actual sample. So the the noise in the sample is going to be very low compared to the signal, we have some evidence here to be able to point us to which path to traverse the graph down. And in fact, what would happen now in say, Velvet, is that Velvet would go and say, okay, my average coverage for each of these k-mers is around about 3. All right, now 1 is much lower than 3, so I'm going to excise all of those nodes, all of those edges from the graph. And it does, it just deletes them from the graph. And that simplifies our graph, which is called graph simplification, and then it just makes one long continuous line and we get our happiness again. Okay, does that make sense to everybody? This is a really important concept, and this is what I was talking about in the tutorial where I said we're going to try and figure out what the coverage cutoff is. This is what this thing is. It's called coverage cutoff. Okay, so if we have a 40x coverage or 40x depth of k-mers on all of our nodes, and a few of them have a coverage of 10, is that low enough? Or does it need to be 1? Well, we can kind of figure that out because we can think about what the error rate might be from our sequencing technology, right? So we know Illumina is pretty accurate until we get up to the 3' end and in really, really long reads, or if something's gone wrong in our sequencing when we've done it. But we have another tool that can help us point in the right direction for that, and that is FastQC. So always when we get sequencing data, we never just throw it into our tools and never think about what's actually going on and just accept the results when they come out blindly. We always actually look at our data and think about the quality of our data and how it's going to affect what we're going to do with it. All right, so hopefully now you're a little bit forearmed when you go to do an actual assembly. You can take your data and look at the quality of it. If the quality is terrible, then you're probably going to have a higher error rate in those reads, which will mean that the coverage cutoff that you need to use when you're cleaning up your graph needs to be higher, which means you may be deleting some signal out of your graph rather than just deleting noise out of your graph. And then that's going to lead to all sorts of problems. Yep. Sorry, Chris? Okay, well, yeah, then the ratio between the signals is going to be one of, if it's diploid, it'll be one of 3 or 4 states, yeah? If there's heterozygosity in that point. And so you're still counting k-mers, and if the ratio between the paths is, say, a half, or what's the other one, 3 to 1 or 1 to 3, then you can probably put it down to heterozygosity. But if it's 0.01 to 99.9, then it's going to be different. No, normally what we do in that case is we'd collapse the bubble, but we'd take a note that we did it for a it was heterozygous at that point, and then annotate, and then we'd annotate the assembly at the end. We'd add a marker onto our assembly in some other kind of file format, like a GenBank file or a genome feature format file, and we'd say, at this point, we found a heterozygosity during the assembly. Does that make sense? Yeah? Okay. So I'm not sure what you mean.
So if you have, at position 1, you have 2 possibilities, you have heterozygosity. At position 100, you have 2 possible.
Oh, yeah, okay, you're talking about phasing of the...
how do you make sure they're on the same strand?
Yeah, good question. Hopefully your reads are long enough to be able to link different points of heterozygosity together, but sometimes it doesn't happen. And so you can't tell which strand has the heterozygous variance compared to the other heterozygous variance. But yeah, you have to do some other kind of read technology to find it out. Right, anyway, getting back to this. So we use this thing called coverage cutoff to kind of look at the frequency that all of our nodes in our graph appear in the k-mers, and then we can make a determination to say that if these nodes here have a frequency much, much lower than the average in the rest of the graph, then perhaps these are errors, right? And we have some evidence to say that they probably could be. And so we can just cut them out of the graph. But if they're of a ratio of 50% or whatever, then perhaps it could be due to the ploidy in our sample instead. All right, so coverage cutoff, what can it do for us? We saw in our previous example, it removes a bubble, it can remove the little tips, it can remove erroneous connections between different sections of our graph. Okay, so if we were reading through, in the bottom one, if we were reading through the top section, and we'd have to break that into 1, 2, 3, 4, nearly 4 different pieces, when actually it's only 2. Okay, so there are a few issues there. And by using coverage cutoff, we can clean up the graph before we start traversing it, and then it makes our life a whole lot easier. All right, one thing I want to talk about coverage depth. We need to remember that we're talking about Kmer coverage here, not read coverage. It's two different things, right? So I've sequenced to 40x read depth, and depending on the ratio between my read length and my Kmer length, I will have a multiple of subsequences of each read in my assembly. And so the actual Kmer coverage depth is equal to the normal coverage depth multiplied by the length of the reads minus k plus 1 over the length of the reads. All right, so here's our general recipe for a de Bruijn graph assembly. We select a value for k, we hash the reads, which is Velvet speak from a long time ago, and because Daniel wrote the Velvet, everyone in the bioinformatics community and just decided to use the word hash to mean break the reads up into Kmers. Then we count the Kmers. So we count how many times each Kmer appears. And then we make the de Bruijn graph, and we annotate the de Bruijn graph with the frequency of each Kmer. And then we perform the simplification steps, and there's a bunch of different ones, but coverage cutoff is our first one usually. And then we read off the contigs from the simplified graph. And hopefully none of that takes too long and doesn't use too much compute. All right, and this is why we want to use de Bruijn. And it's fast, okay? Unlike when we're doing overlap layout consensus, where we have to find generalized alignments between reads. In this time, all we're doing in de Bruijn graph assemblies, all we're doing is we're finding exact matches between the k-1 prefix of one Kmer and the k-1 suffix of another Kmer. And so because they're exact matches, we can actually use a mathematical hash function just to do very, very fast lookups into specific memory addresses in a computer to find whether or not they exist previously, and just add one to that memory position. It's actually really, really fast, and we can build the graph in OMK time, where that's the number of unique Kmers. Right? So it's very, very fast to build. And Eulerian pathing is also very fast. We can build contigs out of our graph in OE time, where E is the number of edges that are in our graph. Because remember, we only have to visit each edge once, right, when we find an Eulerian walk through our graph. And so it's only dependent on the number of edges we have. And so it's also very fast. It's much, much faster than having to do ON squared times OL squared when we're doing overlap layout consensus, especially if we've got 40 or 50 or even 200 or 300 million reads that we have to process. If you're not a computer, yes?
When you're talking about hashing, you're talking about hashing it to like a lookup table, or
Yeah.
is there some sort of non-cryptographic similarity?
No, lookup tables. So basically what I mean by hash is that it's just a mathematical function that takes in the data as a binary string or whatever, runs it through a mathematical function, and then assigns it a memory address based upon the output of that function. And so in this case, the first one, it runs through the hash function, it gets the memory address of 1, and so it adds 1 to that position. The next one gets assigned a memory address of 0, and it gets number 1. and then so on for this one, and then this one here is the same as this one. The fourth one is the same as the first one, so when it runs through the memory function, or the hash function, it gets assigned to the same index as the first one, and so it just increments the number of times it's appeared, and this is very fast because this is just a calculation, straight arithmetic. It doesn't involve doing any kind of alignment. Right, so it's very fast to count the number of reads. And hopefully this hash function here has been designed in such a way that there aren't too many collisions, or there aren't very many times that different types or different sequences here get assigned the same memory address. It can happen occasionally, but a well-designed hash function won't do that. And there are specific ones that we use for genome assembly, for exactly this purpose with DNA strings, and it works really well. Right, de Bruijn compared with overlap layer consensus. I've probably already said most of this, but so what advantages have we found of de Bruijn graphs? It can be built in ON expected time, where n is a total length of, or total number of reads, because remember, to take each read and put it into k-mers, we only have to do that once, and then we only add the k-mers to the graph once, etc. So it can be very fast. With perfect data, the graph is the minimum of either the number of reads or the genome length in time, and when the average coverage is high. So if we have 100x coverage, n is going to be much, much larger than g. And so it actually works in our favour to have more depth. The outcome compares favourably with the overlap graph because we don't have to do all those alignments, where we have the number of reads plus the number of alignments we have to do in time, like building the graph. We need a lot of space to build an overlap graph. We don't need as much when we're doing a de Bruijn graph because we've broken everything into k-mers and we've counted the frequency of the k-mers. Yes, and the other thing we need to remember is not only on plus a time, but a is on squared, so it's n plus n squared. So that's, for the biologists in the room, that's computer speak for it takes a lot longer to build an overlap graph than it does a de Bruijn graph. Okay, so one of the problems that we have with DNA when we're building a de Bruijn graph from it, so we did it with Happiness and we did it with Mississippi, and that was great because it's English and it reads left to right, and we don't have to worry about reading it upside down and back to front. Whereas DNA, because it's double-stranded and reverse complemented, we have to worry about reading it upside down and back to front. And so when we sample DNA, when we take our DNA out of our organism and we chop it up into little bits and we split it apart with using temperature, and then we play around with it and put it in our sequencing machines, we get a random sample from either the top strand or the bottom strand, and we have no idea which one they came from. And so the reads that we're actually building could have come from the forward direction, or it could have come from the reverse complement direction, and we don't know. So when we build the graph of our de Bruijn graph, we have to take that into account, which means that each node that we build has to be the forward strand and the reverse complement strand at the same time. And so it complicates things a little bit, but I'll show you. Okay, so DNA is double-stranded, blah, 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 I've already said that. When we sequence, we randomly get the top and bottom strand, we don't know which. And so we have some k-mers, GGAA, GAAC, etc. And we want to take those and we want to build them into a de Bruijn graph. Now, we need to, when we take each one of these nodes, we split them up into our prefix and suffix, and we add them to our graph. But we need to add both the forwards and the reverse complements of the prefixes and suffixes at the same time. So we do that. So we take our first k-mer and we split it into two, and then we add them as nodes, and then we add the reverse complement to those nodes, and then we draw the k-mers in. Okay, so now you'll notice that we've actually added two k-mers to our graph, even though we've only added we've only taken the first KMA out of our list to work on, we've actually added 2 KMAs to our graph. We've added the KMA GGAA as well as TTCC, okay, because that's the reverse complement of the forward strand. And we repeat it for the rest of the KMAs. So the next one we add is GAAC, and then we add AACT, and then the next one, if you look at TTC, can anyone see TTC up there already? It's in the reverse complement of the second node. And so when we add it, it already exists, and so we have to do this. Okay, so it makes things a little bit more complicated, not too much more complicated, but a little bit more complicated, because when we go looking through the graph to say, does this thing already exist and can I, or do I need to add it afresh, we can just say, no, actually, we need to search for the top strand and the reverse complements to find them. So it's not too much more complicated, but we do have to do things. That one already exists in the reverse complement, and it's already in place, and the same with this one. And so then, because we have a decision to make, we always read the forward strand, well, what we think is the forward strand. We only read in one direction anyway. We'll arbitrarily call it the forward strand. We only ever read off contigs in the forward strand. And so we get these contigs out at the end. Does that make sense to everybody? Hopefully. I don't see anyone shaking their head, so I was, yeah. Yep. Yep. Yeah. Well, it's ambiguous if you go in the reverse complement direction. So when you've got a dual direction graph like this, if you have any kind of divergence or convergence, you have to stop. And that's because you can go backwards, and if you go backwards, the convergence is a divergence. Does that make sense? Yeah, okay. Thanks for pointing that out. All right, so hopefully we talked enough about de Bruijn graphs. Talked about how to build them, why we want to count the number of KMAs, why we want a sequence to high depth when we're doing it so that we can help us simplify the graph by removing our read errors or contamination out of our graph. And then we pull out contigs, and then we talked about, you know, the fact that DNA is double-stranded, etc., and how we go about handling that. Now I'm going to talk a little bit about some de Bruijn graph assemblers. All right, so the one we played around with during the week is called Velvet. It was written by Daniel Zabino and Ewan Burney, who is now still, I think, the director of the EBI in Cambridge. In 2008, well, he started in 2007, but I think he finished the paper in 2008. It has 2 components. There's actually two command lines you have to run. You have to run one called Velvet H, which just takes the reads and builds a giant hash table of them. Yeah, so it makes the KMAs and it very efficiently counts them, all in ON time, just by the number of reads. And then you run another program called Velvet G, which takes the reads that Velvet H hashed into KMAs and takes all those KMAs and builds the graph, and then simplifies the graph and traverses the graph. Originally, he was going to break it into 5 different programs, and it was too hard. So it makes the graph in OU time, where U is the number of unique KMAs. It simplifies it. It makes the contigs in OE time, where E, remember, is the number of edges in the graph. And then here's the thing, it uses a single value for the KMA size. And as we looked at in our tutorial this week, there's a trade-off between connectivity and specificity when we do that. It uses coverage cutoff to simplify the graph. It also uses this thing called expected coverage when you have paired end reads. And the expected coverage is a parameter that it uses to kind of say, well, maybe this contig is repeated in lots of places, and so if it only has 2 connections in and 2 connections out, then I'll just put it between these contigs. But it doesn't really work because it needs to do a whole bunch of other operations that kind of break. But it mainly uses the coverage cutoff to simplify the graph. And as we saw when we ran Devolved Optimizer, it needs multiple runs to optimize these parameters. So we need to run, because every data set's different, we never know what the optimum parameter set's going to be. And if you guess, well, you could come out with a terrible assembly, and there could be a better one waiting in the wings for you just to find. And so we need to search the parameter space for the optimum assembly. All right. And then along came this thing called Spades. It's the Brown Graph Assembler, again. It was out of Pavel Pevsner's group in St. Petersburg. It uses multiple k-mers to build a metagraph. So as we talked about in the tutorial, we actually ran Spades in the tutorial, if you remember. Probably for those who only did it a couple of hours ago, hopefully you do. We picked 3 different k-mer sizes, and then Spades goes and builds a Brown graph for each k-mer size, and then looks for connections between those graphs and builds a metagraph, so that it can use the loop-solving parts of the high k-mer graph, as well as the connecting the disparate parts of our graph in the low k-mer end. And so the final graph, or the metagraph, has connectivity and specificity. And usually we use a low, medium, and a high k-mer size. One of the things it can do, which is kind of okay, is it takes all the reads and sort of bins them and sort of says, well, you know, this one's only one base different to all of the others, and the difference is right up to this 3' end of this read, and the quality score on the one that's wrong is, or the one that's different, is pretty low. So chances are this was a mistake, and so it edits that read and changes it to match the others. Whether or not that's a good thing, don't know. But it can do error correction on the reads first, and so when it takes the k-mers and builds the graph, it has less cleanup that it needs to do. And this is another cool thing it does. At the end of the assembly, it takes the reads that we took the DNA, we broke it up into little bits, then we read part of those little bits, and then we broke up those the reads into even smaller bits again, and then built our graph. Well, just to check for consistency, and hopefully you're at the tutorials where I talked about paired end and how we can use the fact that the read from one half of a pair and the read from the other half of the pair are kind of a known distance apart, and we can map these reads back onto our contigs and see if there's consistency in the relative distance between the pairs. And so if the left-hand pair and left-hand pair and the right-hand pair sort of map around about 700 or 800 bases apart, then that's kind of cool, right? But if they're 15,000 bases apart, then maybe one of them got assembled into the wrong place, and there could be a misassembly somewhere in assembly. Or if they're way too close together, or they're pointing in the wrong direction, that could indicate issues. And so it can use these to validate part of itself, part of its own assembly, and then maybe make some corrections based upon that. Spades is under active development. They're still working on it. I think there's a team of about 6 PhD students and software engineers working on it pretty much around the clock. They release updates to it all the time, and it's making the scope of data that it works with larger and larger all the time. So it can do single cell, it can do metagenomes, which I'm not sure why you want to assemble a metagenome, but people do. It can do metatranscriptome assemblies and a whole bunch of other things. So it's actually a pretty good product, and it's open source and free. And they're very helpful people. I've met a few of them at conferences and things, and normally if we have an issue with something, they fix it pretty much on the spot. So they're actually really cool people. The only problem is it runs slower than Velvet because it has to do all this extra stuff rather than just building a de Bruijn graph and simplifying it. But that's okay. You don't need to run it multiple times. All right. There's a guy who was in the master's course like you guys a few years ago. His name's Ryan Wick, and we were talking about the brown graph assemblers, and how they spit out this incomprehensible text file called the graph file. And when you look at it, it's terrible. And I was lamenting the fact that there was no way of actually looking at this graph file. And then Ryan turned up for the week 2 things and said, "Oh, I wrote this last week. Is it any good?" And it was, and I offered him a job, and he said, "Sorry, I've already got one." I didn't mind. He's working for Kat Holt, who runs a bioinformatics lab at the university, at Bio21. And basically, what this does, it visualises the final assembly graph. So we can see here all of the contigs. These are all contigs, and these are all the connections between the contigs. And so this contig here, you can see, has 3 paths coming into it and a couple of paths coming out of it. The relative width of the contig is the coverage of that contig, or the depth of coverage for each contig. And so you can see this one here is much thicker than these ones, and so it's probably a repeat unit, etc. And these are multiple repeat units that are all joined together somehow, and there's lots of different paths through this graph. But it can kind of help you understand what's going on. And the other cool part about this is you can overlay known sequences across this graph, and it will shade a path through it. So you can sort of say, well, I expect that this organism has this sequence in it because it's a standard gene that every single one of these organisms seems to have. And so it can help you reconstruct paths, etc. So that's quite a nice little tool. All right, so that's the brown graphs with short reads. Remember, our biggest problem with short reads is our repeats. And in our genomes, we have big chunks of genome that are repeated multiple times, and if our reads are short, we cannot resolve those repeats. However, if we have long reads, we can. And there are 2 main technologies still. There's a couple coming along, hopefully sometime in the near future, but at the moment there's 2 main technologies. There's the MinION. It can produce reads of 5K up to about 2 megabases now. Last time I looked, it was around about 10% error rate. So 1 in 9 or 1 in 10 bases that it calls is incorrect, which is quite high. But if you get that long a reads, I'm happy to live with that. But they're mostly indels and homopolymers. The way the micropore works, if there's a whole run of A's, it sort of just zips them all through really quickly, and can sometimes miscount the number of A's that have gone through the pore. It's just the nature of the beast. It's very portable. It's a USB stick if you've ever seen one. They're pretty cool. That was like the selling point of them. Hey, it's a USB stick. You can put it in your pocket and you've got a sequencing machine. All you need to do is plug it into a laptop. And they weren't lying. A friend of mine, for his PhD thesis, put 2 of them into his pocket, and took a laptop bag into East Africa during the Ebola outbreaks, and then sat in a tent and squirted Ebola samples through these MinIONs and sequenced lots and lots of different Ebola viruses. And that was his PhD thesis. It was pretty cool. The only problem was that when he went home, he had to stay in quarantine for 10 weeks and miss the birth of his first child. So his wife wasn't very happy about it. But it's still a pretty cool PhD thesis. And then the PacBio, it's not very portable. It weighs about a tonne. So you kind of need a forklift to move it around, and it's very sensitive to movement. And so the one that we have here at Melbourne University is over in the Peter Doherty building. I think we still only have one in the Peter Doherty building, and they had to reinforce the floor and put in special shock absorbers and all sorts of things so it wouldn't vibrate. But it's a wonderful machine. It can produce reads of about 50 kilobases in length. Once again, there's around about a 10% error rate, but that's becoming much, much smaller. And it has a bunch of advantages in the fact that you can run the same sequences through the machine again and again and again and again, and each time use the previous information to help remove the errors. And so you can get you can get quite high yields and high accuracy out of it in the end, if you run it for a long time. Okay, and last week, I think it was last week, I'm getting confused, we saw why long reads can help us solve repeats. And it's basically because these little reeds here don't span the repeat, and so when the computer goes to put them together, it lumps them all into one. But these ones here, they do span the repeats, and so the computer can say, oh yeah, this repeat is actually anchored into this part of the genome as well as this part of the genome, rather than just having to separate it out and not know where to put it. So these long reads allow us to anchor the repeats into our genome and understand where they belong. And so they can untangle our graphs. So here's the brown graph built from reads of 100 base pairs, and then one with 1,000, and then up to 5,000. And as you can see, we've removed lots of little bubbles, lots of little inconsistencies in our graph, and we've come up with one with only almost a single path. All right, and so this can be the difference between a draft genome and a finished genome. In bacterial world, this is really, really handy. Instead of having that many contigs after a short read assembly, when we have this many contigs and some of them aren't very long and there's still some broken bits, we can go all the way to this. The only problem is this can cost $200, that's probably less than that now, and this can cost $2,000. So you've got to weigh up how much extra information you get out of here, and is it worth it, and what are you going to use it for, etc., etc. And sometimes you'd be just better off doing this. But, you know, it's up to the needs of the experiment you happen to be doing. Okay, so with a move back, with a move to these longer reads where we have less of them, we don't have as many to start with, but we have much, much longer ones, we have less, we can go back to overlap layout consensus. And so recently there's been a whole flood of assemblers coming out that are based on the old concept of overlap layout consensus, because we don't have millions of reads that we need to try and fit into a graph, we only have a few. And so there's a couple of different assemblers that are used regularly now, HGAP and GNU. They both use an OLC algorithm. HGAP is PacBio's software. It's kind of open source, I guess. But you can only you can install it, but you have to download the full package and you have to register with them, and there's some caveats, so it's not completely open source, whereas GNU is completely open source. It's the rewrite of a really old assembler called Accelerate, and they've just updated it to make it work on HPC, which is really nice. So I'll talk a little bit about GNU. It was written by Corin et al. And out of Adam Phillippi's group in the US. Adam Philippi he's a very interesting guy. He used to work in defense in the US, doing all sorts of weird secret squirrel kind of projects, and then decided that really didn't fit his ethics, and so he decided to move out into health research instead, and then helped write this wonderful thing called GNU. So what it does, it corrects the reads before it uses them. So we know that coming off the PacBio machine and the MinION machine, we're going to have around about 10% read error, and that's really, really high. And a lot of them are going to be indels, which make our life really difficult because they produce gaps when we try and do alignments. So what it does, it takes the longest reads, so it puts all the reads together, it orders them by size, and then takes the longest reads to make around about 20 times coverage in depth of our genome. So you need to know roughly how big your genome is, and it subsamples the reads, takes all the longest ones, and says, all right, now I've got enough to make around about 20 times depth of my genome, and then uses the rest to align to those longer ones, and then hopefully, because the errors won't be in the same place each time, hopefully they will correct themselves by using consensus, right, mapping and consensus, which is actually pretty okay. It's a pretty good trick. Then it trims the reads to get rid of any weirdness at the end, and then performs an OLC assembly. And hopefully, at the end of it, you get one config per replicon. Now, the really cool part is that when you install Canoe. If you're ever if you've ever tried to install bioinformatics software onto a Linux machine, you go into this place called dependency hell, which is where each little sub part of the program needs a certain dependencies or C libraries or Python libraries or whatever to run, and a lot of the time they're all incompatible with one another, and you can't have them installed on the same system or they break, and so there's issues, and usually it involves a computer scientist somewhere punching the screen or throwing a wobbly and going home early on a Friday. And so to get around this dependency hell, they really engineered the hell out of this thing, and it's a single command to install it, and it just works. It's beautiful. It even recognises the fact that you've installed it on a high-performance computer somewhere, and it knows about different queuing systems and will submit sub-jobs and things all for you. You just type in Canoe, here's my reads, off you go, and it will nicely play with all of your hardware. It's a really wonderful piece of software. And if you're going to get into bioinformatics software development, this is a really good example. All right, and that is where I'd like to finish. So 10 minutes early, but Doug's got some stuff he needs to talk about. So anyway, thanks. Hope you learned something out of the assembly stuff. Next week in the tutorial, you're actually going to get to write some Python code that will make k-mers out of reads, build a brown graph, and then traverse the graph. Okay, thanks.
Just wanted to thank Simon for accepting this invitation to lecture for us. It's been really, really nice having you here. I learned quite a few things. I hope you guys learned too. And keeping up the momentum with graphs and the brown graphs. So next week we're going to talk about graph theory and network analysis. And also next week is the deadline for submitting assignment 1. I noticed just a couple people submitted. Just make sure you have enough time to do it. If you have any questions, don't hesitate to get in touch with us, with me or Hannah. Okay? Thank you very much and enjoy your weekend.